So today what we're going to do is we're going to look at limits involving infinity again, but this time x is the one that's going to be approaching infinity or negative infinity. So there's only two of these you can look at, right? X can either go to infinity or x can go to negative infinity, okay? And if that limit exists and it's equal to some number, which in this case we're calling capital L, okay? Or if the limit as x approaches negative infinity of f of x approaches some number L, then we say that y equals L is a horizontal asymptote for y equals f of x for the function, okay? So we want to look at these two limits, and if we get a value out of those two limits, then we know that the function is getting closer and closer and closer to that number value as x gets big, or x gets big to the right, which is positive infinity, or big to the left, which is negative infinity, okay? So this couple things I want to look at first are a couple ratios I want to look at, okay? So I want to look at these fractions, okay, which are ratios. If you look at this, we have a numerator of 1, then 2, then 3, 4, and 5, and so on, okay? And what we're looking at is that, yeah, the numerator is growing, right? And it's going up by 1 each time. So from 1 to 2, it went up by 1. It went up by 1. It went up by 1. It increased by 1. You could say it that way too. If you look at the denominator, it grew too, but it grew differently. It grew by a factor of 10. And when I say factor, that means multiplying by 10. So 10 times 10 is 100. 100 times 1,000. Okay, 100 times 10 is 1,000. That's what I should have said. 1,000 times 10 is 10,000. 10,000 times 10, okay, is 100,000. All right. And if you look at the decimal equivalent, we're going to see what's going on. Okay, so 1 out of 10 is 0.1. That's that value of the first ratio. The second ratio, 2 over 100, that would be 0.02. 3 out of 1,000 would be 0.003. 4 10,000ths would be 0.0004. 5 out of 100,000 would be 0.00005. And so if you look, these are getting closer as you look across. These are getting closer and closer and closer to 0. So we can say this: when the denominator is growing faster than the numerator, then what happens is the overall fraction will get closer and closer and closer to 0. Okay, so basically this is it. A number over a big number turns out to be a small number. Okay, so I'll say that in just a second. I'll write that down for us. So for the denominator is growing faster than the numerator. Is growing faster than the numerator. And the value of the fraction is approaching 0. And it would just depend if it's 0 from the left or 0 from the right. It would just depend on if these are positive or negative values. So what I just said, you could summarize, and I'm getting a pen. If we have a number over a big number, then that's going to equal a small number. And when we say a small number, we're talking about something that's close to 0. That's what we mean by that. All right, let's look at the next series of ratios. So this is just the reciprocal of the ones we just did. And if you look, okay, the numerator is growing, so is the denominator. This time the numerator is growing by a factor of 10. And multiplication is more powerful than addition. So that's why, you know, go from one numerator to the next, we're multiplying by 10. These are powers of 10. And then to go from one to the next in the denominator, we're just adding one again. So the numerator is growing, the denominator is growing, but this time the numerator is growing faster than the denominator. And if you look at the values of these, okay, so this 10 over 1, that'd just be 10. 100 over 2, that'd be 50. 1,000 over 3, and this is the only time you're going to see me do this, it's 333.3, because we want decimals, right? Repeating, that's the only time you're ever going to see me do this, okay? And then 10,000 divided by 4 is 2,500. And then 100,000 divided by 5 is 20,000. Okay, and if you look at these values, they're just getting big, right? Now, depending on the combination of positive and negatives, this could either get big positive or big negative, okay? So numerator is growing faster than the denominator, the value of the fraction is approaching either positive or negative infinity. It just depends on the signs of the numbers, okay? But they're getting big, either getting big in a positive way or big in a negative way. So what happens is if we take a big number divided by a number divided by some number, okay, then what we're going to wind up is a big number still. All right. So what we're going to do next is it's called order of magnitude. And what we're going to do is we're going to look and see what functions cause the numerator or the denominator to grow faster than the other one. Okay. And that's what we're going to do next. Okay. So of all the functions, okay, exponential functions they grow the fastest. There's actually one that grows even faster than exponential, and it's called factorial, but we really don't deal with it in Calc AB. We need that more in Calc BC, okay? And so we got to be careful on these because an exponential function, the shape looks like this. It starts out here, and on one side, it's really close to 0. So on one side, it's really small, but on this other side, the right-hand side, it's really, really big. So we need to be careful. It only grows on one side, okay? So we need to, I'm gonna write it in red. Be careful. Only grows on one side. So one side is getting huge. The other side is not. The other side is getting closer and closer to 0. So when you see exponentials, okay, you have to look and see which side of this is. What's the exponent to it? Is it positive? If it's positive, then it's going to be growing. If the exponent's negative, then it's going to be actually getting closer and closer to 0, okay? So exponential functions, okay, and the base matters too. So something like 2 to the x, okay, 2 to the x is going to grow faster than any other function, than any like polynomial or anything like that. Okay, so 2 to the x. E to the x, because e is 2.7 blah, 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 right? It's like the number pi, but that e is bigger than the number 2. So e to the x grows faster than 2 to the x. So if you were comparing these, this one grows faster. 3 to the x would grow faster than e to the x. 4 to the x would grow faster than 3 to the x. So if you were comparing two of these, 4 to the x would grow faster than 3 to the x. and then 5 to the x, and so on. Okay? So this goes from smallest growth to largest growth. 5 to the x is going to grow faster than 2 to the x. Okay? But this is only true for x greater than 0, for positive x's. Okay? So we need to write growth order for x greater than 0. Okay? So all of these grow on the right-hand side. So as x is positive, okay? On the left-hand side, if these were negative x values, then it's not growing at all. It's actually getting closer and closer to the number 0. And all of these do the same thing. They all get closer and closer to 0. All right. The next type of function we need to look at is power functions, okay? That's where you have the basis x raised to a number power. So something like this, x to the 1/2 is going to grow, okay? And it's not going to grow. All of these exponentials grow faster than a power function, okay? So then x to the 1/2, x would grow faster than x to the 1/2 because it's a higher power. X squared, x cubed, x to the 4th, x to the 5th, and so on, okay? This going this way is the growth order. Okay, so as we move across, and x to the 5th is always going to grow faster than x to the 1/2. So if this is in the numerator and this is in the denominator, we're going to have big over a number, and it's just going to get big or small. Okay, now if this was in the denominator and this was in the numerator, now my denominator is growing faster. Okay, so then it's going to go to 0. Okay, and that's how we're going to determine. Excuse me. All right, the last type of function we deal with in Calc AB is functions like this: the natural log function, ln of x, log of x, and these are actually the slowest growing functions there are. They're like the slugs of all functions. Log base 2 of x. Now remember right here, that's a 10, right? And they grow so slow that there is no growth order to these, okay? If you did natural log of x over log base 10 of x, even though this is a bigger base than this one, it doesn't matter, all right? They act like they're the same, okay? So this is log base 2 of x and then log base 3 of x, and it doesn't go in any order. That's why I mixed these up this time, okay? So order sometimes matters on these. All right, so let's go and let's look at some problems on how we're going to figure out these limits based on knowing this idea of which functions grow faster than other ones. Okay, so for this problem, we want to find the limit as x approaches infinity of 5x to the 4th plus 3x squared plus 2x minus 1. So of the things in the numerator that we're adding and subtracting, this has the most power. This grows the fastest. Why? Because it has the highest power. So what we can really do is this is like a millionaire right here, and somebody coming up over here and giving them $1. They won't care that you gave them $1. They're like a million billionaire, right? So this part right here we can ignore, because compared to the growth on this one, this is going to cause some growth, but it's insignificant compared to this one, okay? Because that's the highest power, okay? And then in the denominator, the 3x squared minus 2x plus 1, we can ignore all of that, okay? Because 7x to the 8th, that's a bigger power, okay? So all of these other powers are insignificant compared to this one. This is the one. And you remember in polynomials, when we talked about end behavior in polynomials, we did the same thing, right? We ignored everything else and we just looked at that lead term. That's exactly what we're doing. But now we're looking at a ratio of the two, okay? So now what we can do to figure this out, all right, is this limit, we can say this is the same as the limit as x approaches infinity of 5x to the 4th over 7x to the 8th. So we can use this simplified limit to figure this one out, all right? And then what we can do here is we can reduce this a little bit because x to the fourth, that's going to cancel with 4 of these. So this becomes the limit as x approaches infinity of 5 over 7x to the fourth. Well, look, the numerator is 5. The denominator is 7x to the fourth. This is going to grow, and since it's positive infinity, this is going to get huge, which means this is going to get closer and closer and closer to the number 0 because the denominator is the big thing, right? That's going to be a huge number. Sometimes if it's a polynomial like this, it's pretty easy to figure out, okay? Some other ones, we may plug some numbers in just to verify like what's bigger, right? Okay, and this is kind of easy because that's numerator staying 5. All right, so let's go to this next one, okay? Same idea, and I should have written, we're going to ignore this, right? Those are ignore. And same with this, that we're going to ignore. So from here on out, I'm just going to cross it out, okay? So like the limit as x approaches negative infinity of the same, it's the same function. I'm just going to cross this out because it's insignificant. So is this insignificant. So we want to find what's the limit as x approaches negative infinity of 5x to the fourth over 7x to the 8th. Once again, that reduces. That'd be equivalent to the limit as x approaches negative infinity of 5 over 7x to the fourth, okay? And as x approaches negative infinity, that's just a big negative number, right? This denominator is going to be huge. So that means this is also going to 0. All right, let's go to the next one. So for this next one, we have 3x to the fifth. That's growing faster than any of the other 3 terms, so we can ignore these other 3. In the denominator, these 2 we can ignore. 4x squared is going to grow faster than those. So this is going to be equivalent to the limit as x approaches infinity. And we can use this ratio, 3x to the fifth over 4x squared. And then we can simplify. This means the limit as x approaches infinity of, and then this becomes 3x cubed over 4. Okay, so now the numerator is the one that's growing faster, right? And we're going to infinity, right? So if we're going to positive infinity, when we take that big number and we cube it, that's going to stay positive, right? Times 3, still positive. Over 4, positive. So this is actually going to go to infinity. It's just going to get big. When the numerator is growing faster than the denominator, it's going to go to infinity or negative infinity. In this case, infinity, because this is just representing it's getting bigger and bigger and bigger, but it's positive, right? And when we cube a positive number, it's going to be still positive. Same thing here. We can ignore this, and we can ignore these 2. So this time, this is the limit as x approaches negative infinity of 3x to the fifth over 4x squared. That becomes the limit as x approaches negative infinity of 3x cubed, once again, 3x cubed over 4. If you were doing both of these like this and you went from this to this and you didn't write that because you saw it was the same, that'd be fine, okay? All right, so this time, this is a negative number, right? Or I shouldn't say negative infinity is not a number. It's an idea that just gets bigger in a negative direction, right? But we can help figure out what the sign of this is, whether it's positive or negative infinity, by thinking of this as being like a really big negative number. And when we cube a negative value, we're going to get a negative. Times 3 is going to be negative. Divided by 4, which is positive. So we're going to be taking a negative value, dividing by a positive value. That's going to equal a negative value. And because the numerator is growing faster, this one's going to go to negative infinity. All right. So the left side, if we were to graph this, the left side would be going down and the right side would be going up. All right. Let's do the last one. So for this next one, we can ignore this and this. And we can look at we could figure this out because x cubed grows faster than any of these others. Here, x cubed grows faster than any of the others. We can take a look at the limit as x approaches infinity of 6x cubed over 2x cubed. The x cubes are going to cancel and we're left with 6 over 2. And that would be the limit as x approaches infinity of the number 3, right? Because they're going to cancel. And what happens as x approaches infinity of 3? Well, it just stays. This is just saying it's going to stay 3. Y is going to stay 3. So this is equal to the number 3. Okay. Same thing on this one. We can ignore the 3x squared and the 5x and the plus 1. Down here in the negative 4x squared plus 2x minus 5, we can ignore that. And so we could figure this out by finding the limit as x approaches negative infinity of 6x cubed over 2x cubed. That'd be the limit as x approaches negative infinity of 3. Well, the y is always going to be 3. It's staying 3 on this. And as x goes to negative infinity, the y is just going to stay 3. So this is approaching 3. And that's a way we can figure out using magnitude. Okay? So for this example, we want to identify the horizontal asymptotes for f of x is equal to sine x over e to the x. And we can do this through magnitude, but we need to look at 2 limits. Remember what a horizontal asymptote, as x approaches infinity or x approaches negative infinity, if the function is approaching a number value, then that's telling us we have a horizontal asymptote. If either one is equal to a number value, we are going to have a horizontal asymptote. So we want to look at the limit as x is approaching infinity of f of x, our function. Okay, so to do this, we're going to take a look at what is the limit as x is approaching infinity of sine of x over e to the x. All right, to do this one, I'm going to use a big number to help us figure out what's going on. Okay, so I'm going to pick for this one like x is equal to, let's say 1,000. So what we would have here is sine of 1,000 over e to the 1,000. Now, what do we know about the sine function? Well, the sine function just oscillates between -1 and +1. So this numerator right here is some number. It has to be some number between -1 and 1, because the graph of sine, the highest it gets is 1 and the lowest it gets is -1. It doesn't grow. Okay, so sine function does not grow. It doesn't go to infinity or negative infinity. Okay, it's just somewhere, this value is going to be somewhere between -1 and 1. E to the 1,000 is going to be a huge number. Well, what happens when we take a number, some number between -1 and 1, and divide by a big, huge number, right? That's going to get closer and closer and closer to the number 0, okay? So basically what we have here is a number divided by a big number, and what we get out of this is a small number. Okay, so, and what do I mean by small? It's getting closer and closer to 0. Okay, so this limit would equal 0. Now 0 is a number value, so that's telling us we have a horizontal asymptote. Okay, let's take a look at the other limit that we need to find in order to determine the horizontal asymptote, because you can have at most 2 horizontal asymptotes. So we'd say the limit as x approaches negative infinity, we have to look at this limit too, of f of x. All right, and so this is equal to, all right, the limit as x is approaching negative infinity of sine of x over e to the x. Okay, once again, I'm going to use numbers to help me figure out what's going on. okay? And remember, one side of E grows huge and the other side gets closer and closer to 0, okay? So we would say, let's try something like this. X is equal to negative 1,000. So this would be sine of negative 1,000 over e to the negative 1,000. Okay, so what does e to the negative 1,000 mean? It means 1 over e to the 1,000. So we could do a little bit of math here. And we could actually figure this out right now, okay? Because what is this fraction going towards right here? E to the 1,000 is a big number. We're taking 1 and dividing by a big number. And this just keeps getting bigger and bigger and bigger and bigger because this keeps getting negative, more and more negative. Okay, like negative 10,000, negative 100,000, negative 1 million. This right here is going to go to 0 because the denominator is huge here. Now, one thing we cannot determine, we can't determine whether it's positive or negative because sine of negative 1,000, it's just fluctuating between, it's some number between negative 1 and 1 again. Sometimes this is negative, sometimes this is positive. It just depends on where that is, okay? So what does this mean? This limit will not exist. It's either equal to infinity or negative infinity, or it's bouncing between the two. And in this case, it's actually bouncing between the two because sine is also oscillating between negative 1 and positive 1. Sometimes it's negative, sometimes it's positive. So this limit does not exist. Okay, so what do we know? Does this function have a horizontal asymptote? Yes, it does. It has a horizontal asymptote at y equals 0. So we would say f of x has a horizontal asymptote at y equals 0 because the limit as x approaches infinity of f of x is equal to 0. And that's the definition of a horizontal asymptote. Okay, and you've got to say you have to be able to justify. That's a big thing in calculus, is you have to be able to justify why you're saying what you're saying. And why are you saying there's a horizontal asymptote? It's because of this limit right here. It's because of that. All right, let's go to the next. Again, we want to identify any horizontal asymptotes. So to do this, we need to look at the two limits. So we're going to take the limit as x is approaching infinity of f of x, which is equivalent to the limit as x is approaching infinity of 5x plus 3 over the absolute value of x plus 5, because that's the f of x, right? So I want to see either this or this statement right here on your work, okay? I don't want to see the substitution of what you're going to use to figure this out. So what are we going to use to figure this out? Well, 5x grows faster than 3, so we can ignore this 3. And the absolute value of x is similar to x in that it's more powerful than this 5. So we can ignore this 3 in the numerator and this 5 in the denominator. So we can take a look at this limit right here. What happens to the limit as x approaches infinity of 5x over the absolute value of x? Okay. So one way we can do this, and my work in red is just scratch work, okay? If you could do this in your head, I'd love it, okay? Don't put this is equal to and put numbers in here because that'd be wrong, all right? So this is just to help us figure it out. Okay, so what is a big number that's positive, right? Like 1,000. So this would be 5 times 1,000 over the absolute value of 1,000. Well, what's the absolute value of 1,000? Positive 1,000. So this 1,000 and this 1,000 are going to cancel, and you'd be left with just 5. All right. So this limit, okay, this x and this x, since they're both positive, are going to cancel, and you're going to get 5 out of this, which means you have a horizontal asymptote at y equals 5. All right. And then let's find this other limit, the limit as x approaches negative infinity of f of x. And that's equal to the limit as x is approaching negative infinity of 5x plus 3 over the absolute value of x plus 5. And that's equal to the limit as x approaches negative infinity. Once again, the plus 3 and the plus 5 are insignificant. So we can just do 5x over the absolute value of x. Okay, so this time we need to look at a negative large value. So let's say negative 1,000. So this would be 5 times negative 1,000 over the absolute value of negative 1,000. Well, if I multiply these, that would give me negative 5,000 over the absolute value of negative 1,000 is 1,000. So this would come out to be negative 5. So the answer to this one is negative 5. So we actually have two different horizontal asymptotes here. So f of x has horizontal asymptotes at, and you cannot say 5, you have to say at y equals 5 and y equals negative 5, and you have to give a reason. So because the limit as x approaches infinity of f of x is equal to 5, and the limit as x approaches negative infinity of f of x is equal to negative 5. Okay, I'm looking at my notes from previous years, and I want to point something out. You cannot write this, okay? Don't write f of x is equal to 5x plus 3 over the absolute value of x plus 5, and then write equals 5x over the absolute value of x. Okay, these are not the same. These are not the same. We're only doing this because we're looking at really big values as x approaches infinity or x approaches negative infinity. That's the only time we can use magnitude. Other than that, this 3 and this 5 are significant. It's just they're insignificant when x is really big positively or big negatively. That's when these are insignificant. They're not always insignificant. They're only insignificant when the x is really big. Okay, this is saying that these functions are the same. If you were to graph this one and you were to graph this one, they would not be on top of each other. They would not look the same. Okay? Once again, we want to identify the horizontal asymptotes. All right, so we got to find two limits to do this. We have to find the limit as x is approaching infinity of f of x. That's equal to the limit as x approaches infinity of 5x plus 3 over the square root of x squared minus 3x. Okay, because x is getting really, really big, there's parts that are insignificant. This 3 is going to be insignificant, and this minus 3x is going to be insignificant. All right, because x is really, really big. So we can use this. The limit as x approaches infinity of 5x, because the 3 is insignificant, over the square root, and this minus 3x is insignificant, so it's just x squared. And we should know from last year, this was harped on, right, by me a lot, the square root of x squared is actually the absolute value function. So this is equal to the limit as x approaches infinity of 5x over the absolute value of x. Okay, so x is a positive number, right? So this is going to be a positive number, and when you take the absolute value of a positive number, these are going to be the same sign, right? They're both going to be positive. So we're going to wind up, this just comes out to be 5. And then we want to take the limit as x approaches negative infinity of f of x. That's equal to the limit as x approaches negative infinity. And I'm going to jump all the way to right here. You could even jump to right here, okay? Because this is f of x, right? All right, so 5x. You either got to start it with this one or with this one or the other, okay? And then you don't want to start with this. I will count it wrong. In fact, I'll give you a 0 on it because this is not what you're finding. You're finding this. You're using this to figure this out, okay? So 5x over the square root of x squared. We know this is absolute value of x, so we take the limit as x is approaching negative infinity of 5x over the absolute value of x. Now, this is going to be, x is getting to be big, but in a negative way. So we got to think of this as being a negative number. This is going to be a negative number. This is going to be absolute value of a negative number, which will actually become positive. So these are going to be these are going to be opposite signs. This one's going to be negative. This one's going to be positive. And so we're going to get -1 out of this. And we're going to have 5 times -1. And then that would be -5. All right, so because both these limits came out to be number values, we know that there's horizontal asymptotes. So f of x has horizontal asymptotes at y equals 5 and y equals -5 because the limit as x approaches infinity of f of x is equal to 5 and the limit as x approaches negative infinity of f of x is equal to -5. And that's the rationale of why this has 2 horizontal asymptotes. For this last problem, we wanted to identify the horizontal asymptotes for f of x equals 8 plus e to the x over 2 minus e to the x. This is a problem that gave a lot of students difficulties way back in like 2008 on their AP exam. All right, and it's because they thought of exponentials as always growing, and they're not. Okay, so I want to point that out. One side always grows, and one side always gets closer and closer to 0. Okay, so we got to decide, like, what's happening? Okay, so again, identify the horizontal asymptotes. We have to do 2 limits. The limit as x approaches infinity of f of x. Okay, and that would be the limit as x is approaching infinity of 8 plus e to the x over 2 minus e to the x. And then we want to do this one, and then we're going to figure out what this one is, okay? And then we want to do this one, the limit as x approaches negative infinity of f of x, okay? And that would be the limit as x approaches negative infinity of 8 plus e to the x over 2 minus e to the x. And what is this one going to equal? So I would say when you have exponentials like this, what I would do is plug in a big number and see what's going on. Like x is 1,000, okay? So for this one, if x is 1,000, right, because x is approaching infinity, that would look like this. 8 plus e to the 1,000 over 2 minus e to the 1,000. Okay, so where's the big number here, right? It's e to the 1,000. This is huge. This is huge. So this 8 and 2 are insignificant. And so really this is approximately e to the 1,000 over negative e to the 1,000. And e to the 1,000 over negative e to the 1,000, well, the e to the 1,000s cancel, and you're left with -1. So that means, because we're putting a big number in, this is equal to -1. So this 8 and this 2 right here are really insignificant because this is the thing that's growing. Okay, and I said this earlier, when you have a positive exponent, that's the thing that's growing faster. Okay, so e to a power, and if that power is positive, that's the thing that's growing. It's going to overtake anything else. Okay, even if you had like an x squared or an x cubed in here, this is going to take over. Okay, so how do we go about doing this one? All right, so let me slide over a little bit. Okay, so this would be like putting in like a negative big number, like negative 1,000. So this would be 8 plus e to the negative 1,000 over 2 minus e to the negative 1,000. Now these don't cancel because we're adding and we're subtracting, right? They would only cancel if we were multiplying. Okay, so what does e to the negative power mean? It means 1 over e to the 1,000. So right here, I can replace that with 1 over e to the 1,000. So this is equivalent to 8 plus 1 over e to the 1,000 over 2 minus 1 over e to the 1,000. So what happens here is we have 1 over a really big number. The number 1 over a really big number, and this number, this exponent keeps getting bigger and bigger and bigger, which makes this denominator get bigger and bigger and bigger. This is going towards 0. And so is this one. This one's getting closer and closer to 0. So because these are getting closer and closer to 0, these are now the ones that are insignificant, and the 8 and the 2 are the things that are most important. So this is 8 over 2, which is equal to 4. So that means this limit right here is 4. And once again, we have 2 horizontal asymptotes. So we would say f of x has horizontal asymptotes at y equals -1 and y equals 4 because the limit as x approaches infinity of f of x is equal to -1 and the limit as x approaches negative infinity of f of x is equal to 4. And let me slide that up so you can read it. Okay, so f of x has a horizontal asymptote at y equals -1 and at y equals 4 because the limit as x approaches infinity of f of x is -1 and the limit as x approaches negative infinity of f of x is equal to 4. All right, so hopefully this kind of helps you. And I gave you some difficult examples to get you the idea of, okay, what's growing. If you get stuck, you can always plug in a big number, okay? You can always plug in a big number and like help you see which thing is the thing that's growing, especially with these exponentials, okay? All right. In years past, I've given a problem very similar to this on the test, okay? All right, to see, are you paying attention to, is that exponential? Is the exponent positive or if it's negative? If it's positive, then it's going to grow. If the exponent in the exponential function is negative, then it's getting closer and closer to 0 and it's insignificant. It's like adding 0, okay? Like right here, this is like adding 0, okay? It's really, really a small number. You're taking 8 plus a number that's really close to 0. All right. That's it, guys, on horizontal asymptotes. This is kind of the hardest part of this, I wouldn't say the course, of this unit, okay, is the vertical asymptotes and the horizontal asymptotes and the justifications, because we're not really used to of justifying why our answer is what it is, okay? And this is actually a simple one to justify, okay? But we're just not in the habit of doing that, all right? And that's part of the preparation for the AP exam is, and even just math in general, is you're able to create an argument based on definitions, and this is the definition of a horizontal and vertical asymptote. Okay, all right, you guys, that's it for today.